Building effective AI solutions requires a structured approach rather than coding blindly. Staring at a blank screen and typing leads to errors and wasted time. Instead, developers rely on a cyclical, six-stage blueprint designed to accurately solve real-world problems. Imagine a farming community facing financial ruin. A mysterious disease is spreading rapidly through their crops, destroying the harvest. Our task is to design an AI system to identify and halt this disease. Before starting the cycle, we must determine our data type by selecting an AI domain. We have three choices: statistical data for numbers, computer vision for images, or natural language processing for text and speech. To monitor fields, we process drone images, meaning we need computer vision, enabling machines to interpret physical visual information. Selecting the correct data domain and committing to a rigorous development cycle ensures the system is tailored to fix the decaying crops, rather than burning through resources on the wrong solution. Stage 1 is problem scoping, using the 4Ws problem canvas. Who is affected? Farmers. Where it arises? Agricultural fields. Next, what is the issue? Physical decay of crop leaves. Finally, why solve it? To prevent financial ruin and ensure food security. With the scope locked, we move to Stage 2, data acquisition. AI models depend entirely on the raw data fueling them. If we collect blurry, inaccurate images from our drones, the resulting AI will perform poorly. The strict rule is garbage in, garbage out. We also apply a value-based ethical framework during this collection. Flying drones over private farmland requires explicit permission and strict protection of the privacy rights of the residents living there. A perfectly scoped problem canvas holds no value if the data gathered to solve it is legally compromised or factually useless. Stage 3 is data exploration, the process of visualizing this massive dataset. By plotting the drone data into charts and maps, we can identify an underlying visual trend, distinct brown spots appearing consistently on the dying plants. That pattern leads us right into Stage 4, modeling. We feed our explored charts and images into a selected algorithm, allowing the machine to analyze the patterns and begin to learn. Developers choose between rule-based models, which strictly follow a human developer's pre-written instructions, and learning-based models, which dynamically adapt and figure out the rules themselves based on historical data. Once the model is built, we arrive at Stage 5, evaluation. Before handing it to the farmers, we must test its accuracy. Should we test using the same training images? No. To prove it predicts disease, we evaluate against unseen data. Finally, Stage 6 is deployment. The model transfers into a smartphone app. As farmers scan crops, fresh data feeds back into the system. The launch is a trigger, not an endpoint. Post-deployment monitoring ensures the system catches new variations of the disease, making this a continuous, living cycle of improvement. This framework applies to entirely different industries. Consider the process of building an automated email spam filter. The data type shifts from drone imagery to written text, which means our chosen AI domain must switch to natural language processing to read and decipher human language. The cycle remains exactly the same. We scope specific types of spam, acquire verified inbox data, explore text for hidden word patterns, run text through a learning-based model, evaluate its accuracy on unseen messages, and deploy it to live inboxes to protect users. This graphic shows the complete technical blueprint. At the center is the 6-stage cycle. On the left are the 3 data domains. On the right are the 5 ethical principles that must guide every developer: non-maleficence, beneficence, autonomy, justice, and transparency. Technical mastery is achieved by following this cyclical, ethical framework to build technologies that safely and effectively serve human needs.